This video is called The Basics of Dilations, and what I want to show you is how you dilate a graph. Which one do you like best? X squared, square root, or absolute value? You tell me. Can you tell yet which parent function I'm graphing? Does this contain 0, 0, and 1, 1? Does this? Does this? Yeah, all I have is 0, 0, and 1, 1. What's 0 squared? What's 1 squared? What's the absolute value of 0? Absolute value of 1. Square root of 0? Square root of 1? 1. So really, all three parent functions go through these 2 points. True or false? True. But here's how they differ. On the red one, the next point is 2 squared. What's that? 4. And the next one is 3 squared, which is 9. So x squared curves upward and looks like that. What happens on the other side of the axis? Same thing. That's the parent function x squared. Good? Next, the absolute value differs because it doesn't get squared. It's just the absolute value of 1, 1. The absolute value of 2, 2. 3, say 3. 4, 5, and that's all it does. Could you say that on the right side, that's the graph of y equals x? Y equals x. 1, 1, 2, 2, 3, 3. Y equals x. Whatever the x is, the y equals it. On the left side, however, the absolute value of -1 is 1. The absolute value of -2 is 2, -3, -4, -5, 5. On this side, it's y equals -x. That's why in some books, you'll see the absolute value written this way, as a piecewise function. It's x if x is greater than or equal to 0. It's -x if x is less than 0. You can rewrite an absolute value as a piecewise function. We didn't study that specifically in this class, but you can. All right? If you're worried about that, forget about it. Next, we have the square root function, and that's the only one without symmetry. See, the red graph has vertical symmetry, so does the green one, but the blue one only goes in one direction. What's the square root of 4? Just 2. What's the square root of 9? 3. No more plus minus. So it goes like this. We don't draw the square root of 1, -1, the square root of 4, -2, and the square root of 9, -3, because if we did, it wouldn't be a function. We only draw the top half. So those are our 3 parent functions, and now we're going to see how to dilate them. And the one that I'm going to dilate is x squared. All right? So if you ever need to go back and review your parent functions, this would be a good video to watch. Now we're going to look at our first basic dilation, and what you might see is it written like this, which is odd because we don't normally write things over there with the y. If they do, I want you to take it over to the other side of the equation by multiplying both sides by 2. So I'm going to show you how 2x squared differs from x squared. What this creates is a vertical dilation. And it takes all of your y coordinates times 2. So instead of being 0, 0, it's 0, comma, 0 times 2. Uh-oh, that's still 0, okay? All the y coordinates, by the way, on the parent function, the y coordinates were 0, 0, 1, 1, 2, 4, and 3, 9. They would look the same on the left side, except the x's would be negative. What a vertical dilation of 2 does is it multiplies all of these y's times 2. So 1, 1 would become 1, comma, 2. 2, 4 would be 2, comma, 8. And 3, comma, 9 would be 3, comma, off the screen. What is it? 18. So the parabola gets skinnier and taller because of that dilation. The next point would be up here at 318. You know what happens on the left side? The same thing, but negative. Negative 1, 2, negative 2, 8, and negative 3 off the screen. That's what a vertical dilation does to that parabola. Are there any questions? I'm going to rewrite how that problem started. It started as y over 2 equaling x squared. So the y was divided by 2, and the y's got taller by 2. Okay? Now we're going to do in green, y equals, what if it's the x over 2 squared? Here's what happens. Ready? When the x is divided by 2, instead of doubling the y's, it actually doubles the x's. You know how with x, everything seems kind of backwards? X minus 3 is right 3. X plus 2 is left 2, right? Well, it's the same way here. When x is being divided by 2, it actually doubles the x's. Check it out. Instead of 0, 0, you would double the x and still get 0, 0. It doesn't move. Instead of 1, 1 in red, double the x. What would it become? 2, comma 1. 2, comma 4 is going to get dilated because of this by doubling the 2. 4, 4. 3, comma 9 will be 6, comma 9. What was I? 3, 4, 5, 6, comma 9. And the parabola gets wider because of this dividing by 2. It works. Try it. Put in 6. Did you get 9? What's 6 over 2 squared? 9. It works. The opposite action creates this reaction. Dividing by 2 widens it. Question? Continuing with this green one, what would you get here if you squared the top and squared the bottom? 4. The green one, well, we said it doubles the x's. We could have graphed the green one by cutting the y's by 4. Look, this point is 2, comma 1. Now I might make it go here for a minute. Ready? Here we go. Ready? 2, comma 1 was 2, comma what on the red one? What's a fourth of 4? 1. Oh, it went away. It's back. Not back. Go back. There you go. 2, comma 4 becomes 2, comma 1 because you cut it by 1/4. What you'll find with parabolas is you can either widen the x's or shrink the y's. Or you could make the y's taller or shrink the x's.